Paper 2 smells like anxiety, terror, and dread. Paper 2 makes paper 1 look like an infant with a big spoon. No threat, no danger. But paper 2 is like a wolf with an MG42, and he's gonna blow your house down. I suppose what I'm trying to say is paper 2 is very, very, very heavy. Section 2.1 Algorithms. Section 2.1.1 Computational Thinking. We're going to be looking at abstraction, decomposition, and algorithmic thinking. First, let's start with the letter A for abstraction. What's the definition of abstraction? It is removing or hiding unnecessary detail.
That's unnecessary.
Focusing on the important detail. And the benefit is that it simplifies the problem, reduces complexity, and makes it easier to understand. An example of abstraction that OCR love to use is the following. Imagine somebody wanted to make a system that scored the number of goals that their favourite team got.
Meat pie sausage roll, come on England, gives a go. Meat pie sausage roll, come on England, gives a go.
Now, a method of abstracting that would be to remove unnecessary detail, like player names, or player addresses, or player hair colour, or any other detail that would be unnecessary to simply getting the number of goals. Decomposition. Decomposition has got nothing to do with food rotting in the ground. But everything to do with decomposing, breaking down a big problem into smaller problems. This is the definition. Decomposition splits the problem down into sub-problems. It makes it simpler to understand and maintain. You can tackle each sub-problem independently. An example of decomposition would be if you were making a Minecraft clone, you could break down that task into 4 sub-problems: making the graphics, making the physics, making the inventory, and making the network features. Finally, algorithmic thinking. This is very much based on common sense and a strong use of your brain.
This is big brain time.
Basically, algorithmic thinking means thinking logically. Now, you're thinking, Mr. Singer, how do I apply that in an exam? Well, young scholar, for example, if the exam question said to you, you need to make a program that adds 3 numbers together, calculates an answer, and outputs it, algorithmic thinking would be thinking, oh, okay, I need 3 variables for my numbers. I need to use an input statement to get them in. I need to add them up using the plus sign, and then I need to output them using the print statement. Boom, bish, bash, bish, bosh. You've just done algorithmic thinking. Well done. Section 2.1.2 Designing, Creating and Refining Algorithms. The first part is identifying inputs and outputs. Calm down, it's going to be alright. Calm down. Jeff! Calm down, it's going to be alright. What's the matter? I can't figure out what input means. It's alright, Jeff. An input is something that goes in to the computer. In Python, we use the input keyword for this. A real-world example would be typing words into your computer on Google, for example. Output is even easier. Get this. Right, Jeff, listen to me. It's all right. It's going to be okay. Jeff, stop making that noise. Outputs are stuff that come out of the computer. In Python, we use a print statement to do an output. But a real-world example would be the monitor that you're looking at right now, or your phone screen, showing you the search results that we asked for in the previous example. So if you've Googled speed of a cheetah and it's outputted something on your monitor, it's an output because it's come from the PC out to a different device. Another example would be a printer. If you print something off, you're going out from the computer to the printer onto the piece of paper, going out. Now, an example that OCR like to use with this is the following, and you're going to love this, big brain gamers. A teacher researches the length of time students spend playing computer games every day. Honestly, it's not me. The teacher asks students how long they spend completing their homework. Students answer in minutes and hours. For example, 2 hours and 15 minutes. The teacher would like to make an algorithm that will display the students' inputs in minutes only. Identify an input and an output required for the algorithm. Now, this is a 2-mark question straight off an exam paper. What would the input be and what would the output be? Now, I would argue the input would be the number of hours and minutes that little Jeff, not the same Jeff as before, this is a different Jeff, the number of hours and minutes that Jeff spent playing Apex Legends or Fortnite, and the output would simply be the number of minutes, because that's what we wanted to output. Structure diagrams. A structure diagram is a simple visual way of doing decomposition. We just looked at this. Now, to do this over audio is going to be very difficult, but I'm going to try my best. Imagine a diagram with 3 levels. The top level being the least specific, and the bottom level being the most. We use what's called stepwise refinement to make our structure diagrams. Now, I'm going to give you an example that you can visualize in your head. Let's think of a program with 3 levels. Top level, level 1, and level 2. The top level would be the company wage program. If we wanted to make a program that tracks the paychecks and the wages for our employees. Company wage program. Level 1, we decompose it down into the next few sections. We could have one section for inputting employee details, one section for calculating pay, and another one for producing pay slips, all on level 1. Now, if we go down another level to level 2, we can fork off calculate pay, and we could separate that, decompose it essentially into 2 more subsections. We could have calculate gross pay and calculate deductions, like for example, fuel costs and whatnot. Going off the producing pay slips decomposition, we could have even more below that. And most structure diagrams you come across in the exam will only be 3 levels. So that's all you've really got to worry about. Flow charts. Think of flowcharts as a visual way of doing pseudocode. That's the easiest way to think about it. Now, what does every flowchart start with? That's right, a terminal. A terminal is like a rectangle with rounded edges, looks like a pill. At the start of your flowchart, you're going to have a terminal that says start. And at the end, you're going to have a terminal that says, you guessed it, end. Now, what goes in between the start and the end, you might be thinking? Well, there are a few shapes that you need to memorise. First one, nice and easy, is decision, represented by a diamond. That sounded bad. Diamond for decision. Diamond for decision. A diamond for decision. Whenever you see a diamond, that's when we make a decision. Usually, you'd write an if statement inside there. So, for example, if the person's age is over 18, we could serve them an alcoholic beverage. If they're not, then we wouldn't. The next shape is a slanted rectangle or a parallelogram. This means input or output, depending on the circumstance. So, for example, if you wanted to input a number, because it's a maths program you're making, you could do a slanted rectangle and put input, first number, and then do another one, input, second number. And if you wanted to output what they add up to, you could do a process and then do an output with the same slanted rectangle and say output answer. The most important, but probably hardest to remember, is the process. The process. Now, very easy shape. Process is represented by a rectangle, a regular old rectangle. And inside there, you can basically summarize any function. Let me explain. Let's use the maths example from before. If we'd inputted 2 numbers from the user, we could have a process called add numbers together, and we could write in that square box, answer equals num1, add num2. Boom. We've done it. Anytime there is an action, anytime something is actually being done, you're using a process. Here's some ancient Greek for you. Pseudes. Pseudes or pseudes. This means false. And it's ironically where we get the word pseudo. Pseudocode. Pseudocode is false code. It's not real. It doesn't have real syntax. However, it does have a general structure that I'd like to go over with you. In the exam, remember this, you will be asked either to write what you're doing in pseudocode or a high-level programming language. Now, what language are you going to use if it's the high-level one? Python, that's right. But if we have to use pseudocode, you better know what you need. Start with the basics. In Python, a single equals would mean assign, to give something a value. Num1 equals 10. We're assigning num1 the value of 10. But in pseudocode, we'd use an arrow to show that the value is going from 10 to num1. So the pseudocode would be num1 with an arrow pointing to num1, 10. In Python, we might say print to do an output. In pseudocode, we would say display or output instead. Because when my nan reads the word print, she doesn't think of something coming up on a screen, does she?
If my nan can't understand it, it ain't pseudocode. Sus.
She thinks of paper, and we aren't using that. Input's an easy one. It's the same in Python as it is in pseudocode. Input means input. Easy peasy lemons. A while loop, or any loop really, can be replaced with repeat until, or just repeat, or you could even say while. It's quite open-ended, to be honest, as long as it makes sense to you. Equals in Python is used for comparisons, like if num1 equals num2, print num1 is equal to num2. But again, simplify it, a single equals is used for this instead. Finally, if is if. Easy peasy lemons. That's pseudocode. The next part of the spec talks about high-level programming languages, but I can't cover all of Python on an audio recording. Revise Python. Do the training course I've set you, or you are going to be stuffed in the exam. Practice, have fun, make some games, make some beautiful things. Let's move on to trace tables. The way a trace table works is, as your program is going through, variables change their value. A trace table allows us to track the value of certain variables at certain points in the program. Take, for example, a basic piece of code. Let's say we have 3 variables, num1, num2, and answer. Let's say that we set these all to 0 at the start of the program and add them in as the user types in the numbers and we add them together. At the start of the program, in step 1, answer is going to be equal to 0. But once num2 plus num1 equals answer, the other way around, sorry, is called, what's going to be the value of answer? Num1 add num2. And we'd show that in our trace table. Take a look in the revision guide if you want any more help with this. It's very visual.
Where are you, Deborah? Deborah! Deborah! Can't find you. Deborah!
Philip can't find Deborah, but with a binary search, we can find the data that we're looking for. The binary search algorithm is the first one we're going to look at out of 2. We're going to look at binary and we're going to look at linear. Now, binary, like a bicycle, it means 2, and obviously half, 1 over 2. We're going to halve the data every time. This is how it works. The binary search, number 1, can only be done with sorted data. That's the disadvantage. Can only be done with the data has to be in the right order for us to be able to do this. Second, it works by finding the middle element in a list before deciding which side of the list the desired element is to be found in. For example, if I was looking for somebody with the last name beginning with T, like Trent, and I've got a full list of people going A to Z, is my data going to be in the first half or the last half? The last half, well done. Hola, soy Dora. The unwanted half would then be discarded to, A up to whatever the heck the middle letter of the alphabet is. And the process is repeated until the element is found. Now again, advantage, very, very, very fast. But the disadvantage is it can only be done with sorted data. Linear search.
Excuse me, are you my mum? Okay, thanks for your time. Excuse me, are you my my mum? No, thanks for your time. Excuse me, are you?
You get the idea. We keep going through every element and checking if it matches what we're searching for. Now, this is very, very easy to program because it's like, is what I'm looking at what I'm searching for? But it's very slow. As you can imagine, poor Philip wouldn't find his mum potentially in 7 billion tries, because how many people are there on Earth now? Like 8 billion? It's going to take him a long time. So, definition. Linear search literally goes through the list from start to finish. If the current item it's looking at is equal to the search term, the search is done. It's that simple. Again, disadvantage, it's very slow. Advantage is, it's very easy to program.
Sort your life out, Philip.
No, Deborah, no.
Sort it out, Philip.
No, Deborah.
Philip can't sort his life out, but we can sort our data sets, and there are 1, 2, 3 main ways that we can do this. The first way is with what's called a bubble sort. Now, remember the Hungarian dancing? A bubble sort compares pairs that are next to each other. If they need swapping, they get swapped. Now, the benefit of a bubble sort is that it's very easy to program. And this is obvious, but the data doesn't need to be sorted, of course. Negatives. It's slow and it's very inefficient. If we've got like 1,000 records, we could potentially be doing like 1,000 swaps, which is just crazy. This is the way a bubble sort works in 5 steps. Number 1, start at the beginning of the list. Number 2, compare the first value in the list with the next one up. If the first value is bigger, swap the positions of those two. Number 3, move the second value in the list. Again, compare this value with the next and swap if it's bigger, and just keep swapping until there's no more items left. Then go back to the start of the list and do it again. Every time we go through the list, that is called a pass. The next sorting method that we're going to look at is called the merge sort. The benefit of a merge sort is it's very, very fast and efficient. The negative is it's extremely hard to program. A merge sort uses a technique called divide and conquer. Sounds like Henry VIII or something. The list is repeatedly divided into 2 until all the elements are separated individually. Pairs of elements are then compared, placed into order, and combined. This process is then repeated until the list is recompiled as a whole. Make sure you look at the revision guide for this. I've got a good visualization and a link to a great video. Insertion sort, Number 1. An insertion sort compares values in turn, starting with the second value in the list and comparing it with the first. Similar to a bubble sort, similar to a merge sort. It's kind of a hybrid, really. If this value is greater than the value to the left of it, no changes are made. Of course, because it's on the correct side. Otherwise, the value is repeatedly moved left until it meets a value that is less than it. So it needs a swap. The process then starts again with the next value and continues until the end of the list. Again, the benefits of a merge sort are it's middle in terms of speed. It's not as slow as a bubble, and it's not as fast as a merge, and it's like middle difficulty to program. The negatives are that it's not as easy to program as a bubble sort. Section 2.2 Programming Fundamentals. Section 2.2.1 Programming Fundamentals. That's the same name. Thank you, OCR. Let's start with the bread and butter basics. Variables and constants. A variable, here's the definition, is a name or identifier for a memory location that can change its value while the program is running. One more time. A variable is a name/identifier for a memory location that can change its value while the program is running. Constant is very, very similar. But before we do that, let's do an example of a variable. Num1. Name. Fave potato type. Mashed, baked, or jacket, whatever it might be, we can store it in a variable as long as it's going to be changing while the program runs. Now, the other half of that coin is our big juicy friend, the constant. A constant is a name/identifier for a memory location that cannot change its value while the program runs. Cannot, I can't do it! A constant cannot change its value while the program runs. So the definition is virtually the same for both of them, but the end is a little bit different. Next, we're going to look at program flow. Sequence selection, and you guessed it, iteration. Let's look at sequence first. Now, I'm going to give you the simple definition and then the OCR specific definition because they don't sound similar at all. Sequence is where our program has to do what it's doing in the right order, or it won't work. For example, if we had a program that adds two inputted numbers together, but we did the addition before the input, that would be out of sequence, because we haven't inputted it yet, have we? No, we have not.
Billy, put the pie in the oven. Eat the pie and cook the pie. Make the pie.
Deborah, that's not going well. That's out of sequence.
But OCR's definition is, oh, you're going to love this. A control structure is where the computer executes every instruction in the order in which they are written. A control structure where the computer executes every instruction in the order in which they are written. Yeah, basically, write the program in the right order. If you saw a program that was like, if it was out of order, it'd break, then that's a good chance that it's using sequence. And in the exam, you'd probably get some code, and it'd be like, identify which of the three program flow methods this program is using. And you'd have to say, selection, sequence, or iteration. That's right. Selection. Again, I'm going to give you the basic definition first. Selection is if statements. If you see an if or an else or a case, you're dealing with selection. Because you're saying, if this happens, we're going to do this. If this happens, we're going to do this. In this case, when this is true, do this. We're selecting what code to use.
You need to choose, Philip. Is it me or that pie?
I choose the pie, Daddy. The pie doesn't complain.
But OCR's definition is a control structure which has instructions that do not have to be executed in sequence. It is non-sequential.
Philip! Every time I see you,
You're playing Fortnite like a sweat.
you keep repeating your mistake. You're doing it over and over and over again.
I'll do what I want, Emily. Can't tell me what to do.
In the same way that Philip keeps repeating his mistake, iteration is when we keep repeating a process. If you see a for loop or a while loop, you are looking at iteration. Iteration means for or while. Iteration means for or while. Iteration means for or while. I can't stress that enough. If you see iteration, you think for or while. If you see selection, you think if statements. And if you see sequence, you think do it in order. It's very, very simple. Here's the OCR definition for iteration. A control structure which repeats a process until a condition is met. Remember, reiterate, the phrase reiterate means to do again. Iteration is loops. And in Python, we use for and while to do iteration. The common arithmetic operators, or in basic speak, the symbols that we use to do math. So, big brain time. It's big brain time. Addition is a plus. Subtraction is a minus. Star is for multiplying. / for division. Mod for modular division. Div for quotient division. And a little like arrow floating in the air pointing upwards. They call it a caret to show an exponent like 2 to the power of 4. If you're wondering what mod and div are, modulus and quotient, mod returns the remainder after a number is divided. So mod gives us the remainder. And div gives us the quotient, the integer portion of a division. So for example, if 5 was divided by 2, we'd get 2 instead of 2.5. Let's look at the Boolean operators. There are 3 basic operators, and, or, and not. Now, these can be used in logic gates, and they can be used in selection. For example, if I had a program that said num1 equals 7, so initializing an integer with the value 7, and then I had a selection statement that said if num1 is greater than 10, or num1 is equal to 5, print hello. I've just used a Boolean operator in my selection statement. But we can also use these operators with the logic gates. The first logic gate, and the easiest one to remember, is the AND gate, and it looks like a big capital letter D. This can only be true if both inputs are true. If A and B are true, C is true. Otherwise, it's 0. Or looks like an arrowhead. And as long as one of the inputs is a 1, we get a 1. This or this. The NOT gate is like a triangle with a circle on the end. If a 0 comes in, a 1 goes out. And if a 1 goes in, a 0 goes out. Doth thou get me? Section 2.2.2 Data types. The big 5 data types. If you don't know this by now, I can't help you. Let's go over them real quick. Integer is a whole number, so no decimals. Float, or real, as it's sometimes called in the exam, is a decimal number. A string is a collection of characters or text. Character is a single character. That could mean any number, letter, or symbol that you see on a keyboard. And finally, Boolean. This can either be true or false. True or false? Section 2.2.3 Additional Programming Techniques. The first one we'll look at is something called string manipulation methods. These are methods that manipulate strings. That was hard. Basically, right, they're methods that manipulate strings.
Brother, this guy stinks!
Yeah, that was tough. Alright, I'll stop. For example, if we wanted to use the dot upper method on our string, let's say we got a string username, and it's the username that the user has inputted into our system. If we wanted to turn all of those letters uppercase or lowercase, we could use the dot upper function or the dot lower function to turn it into something different. There are some other methods as well, like dot length, which would tell us the amount of characters that are in the string. Dot reverse, which would reverse the string, you know, so if it said singer, it would now say regness. Yeah, regness. We could use the square brackets from the array to pick out certain parts of a string. For example, if I had a string that had the name dog in it, called my favourite animal, if I wrote print my favourite animal square bracket 0 square bracket, it would output the letter D, because that's the first element in that array. There are tons of these, and in the exam they might ask you to use any of them, so it's worth just having a general knowledge, but it'll probably be a coding question. Oh, scary! File handling. File handling, right? Basically, that's where we handle files, you know? Opening a text file, saving a text file, reading a text file. All that stuff in the exam. Fortunately, it'll pretty much always be a text file. You're not going to be expected to understand how to decode an MP3 or an MP4. That would be crazy! Even though this is OCR that we're talking about. Now, there are 4 main functions, I believe, because at this point in time on Monday, the 12th of December 2022, they have not actually released any file handling questions yet. Thank you, OCR. But I believe this is what will come up. Could be wrong. Let's find out. Open is a method that opens the file into the program. So you have your file handler variable, for example, my file, and you could open your text file into it. For example, file handler equals open, and then do all the syntax or whatever, my text file.txt. And that'll whack it into the file handler so that we can see it and mess with it. The read function, which will read a file into a string, you can either use read or read line in Python. Read will read the whole thing, and read line will read it line by line. Then you've also got write, which writes text to the file handler. And then this is the important one, close with some brackets. Close. This saves it and closes it. So if we don't do this, it won't save. Maybe in the exam, they'll show you some code and it'll be like, will this save to a text file? And it's missing the close. And you have to notice it. But there you go. File handling.
Oi, Philip, what you doing with them eggs?
Deborah, it's a collection of eggs. I've got a collection of eggs. They're all the same type of egg. And I can't get any more. And I can't add any more. This egg box cannot grow over time.
Just like Philip's egg box, an array is a collection of data that has the same data type. For example, all of the data type must be strings, or all the data types must be integers. An array is static, as it uses a static area of memory. Think about a static caravan. It doesn't move, it doesn't grow, it doesn't get any bigger. So, when we make an array, we have to say how big the array is going to be. For example, 5. And also what type of data that it's going to hold. An array, therefore, cannot grow over time. You can't append data to it. Let me give you an example of declaring an array. Fave colours. That's going to be my array name, equals square bracket, square bracket, square bracket, red in quotes, blue in quotes with a comma in between, another comma, green in quotes, and then we end with a square bracket as well. If I wanted to print red, how would I do that? Well done. Hola, soy Dora. Print, bracket, normal bracket, fave colours, square bracket, 0, square bracket, normal bracket. Because 0 is the first element in my array. Remember, we start from 0. 2D arrays. A 2D array is an array of arrays, a collection of collections. Allow me to give you an example. Imagine we wanted to store an array of people's names and their ages together. For this, we would need a 2D array. The way we would do it is we'd have an array called, for example, names and ages. We do an equals and we do a double square bracket. Then we'd have the person's name in quotes, Philip, for example, end the quote, do a comma, and then have the age. Now remember, this is an array of arrays, so even though the data types are different across the two different arrays, that's okay, because each array still has the same data type within it. It's okay. I'd then have a square bracket to end it off and a comma to separate where we're storing these different sets of arrays. At the very end, I'd finish it with a square bracket. If I wanted another person in that array, I could obviously add it. Let's say my array contained Philip, age 45, and Deborah, age 49. Deborah's 4 years older than Philip. If I wanted to access the number 45, which is in Deborah's, I would have to do print fave colours, brackets 1, end bracket, brackets 1 again, end bracket, because that's going to print element 1, because remember it starts at 0, which is Deborah, and position 1, so not her name, but her age. 2D arrays are a bit funky and they're a lot easier in person. Make sure you use the revision guide if you get stuck.
You're always at work, Philip.
What do you mean, Deborah?
You're always at work. You never call me. Call me, Philip. Call me.
In the same way that Deborah needs to be called by Philip, a subroutine needs to be called to run. A subroutine, by OCR's definition, is a mini program within a bigger program. It sits in the background waiting to be called. Waiting to be called. Waiting to be called. There are two types of subroutine. There are functions and procedures. Now listen closely, because they will ask you for the difference in the exam. A function is a subroutine which returns data. Returns data. Returns data. It returns data back to the program. Function returns. A function returns. A function returns. A procedure is a subroutine which does not return data back to the program. Does not return data back to the program. Does not return data. Does not return data back to the program. Please understand me. Please. If you see a return statement, you're dealing with a function. If you don't, you're dealing with a procedure. Both are subroutines, but they are different. Okay. Next, parameters. A parameter is anything that we pass into a function, really. So if I defined a function, let's have a look at the code. Add two nums, so def add two nums, bracket x comma y, bracket colon, and I make an answer variable, answer equals x plus y, and I return the answer. What were the parameters there? It was the x and the y in the brackets. The x and the y in the brackets, because that is what's being passed in to the function or the procedure, whichever one you're using. By the way, pro tip, x and y would be the parameters. But if, for example, I called the function and passed in 3 and 5, so I'm expecting the number 8 to come out because 3 had 5, the 3 and the 5 would be considered arguments. Arguments is what Deborah and Philip do a lot of. Arguments. Okay. Parameters are the names themselves, x and y, and the arguments are the numbers that we actually pass in. Boosh. Let's get into databases. Databases are made of tables, and every table contains records and fields. Now you're going to say, Mr. Singer, what the flip is a table, a record, or a field? Let me educate you, young scholar. We could have a table called Minecraft items. That table could contain a record called wooden sword and a field name called damage amount, if we wanted to. If you wanted the full table, we could have item ID, which would be an integer, 0, 1, 2, 3, 4, 5, 6, 7. We could have item name, which would store the name of the item, for example, wooden sword, diamond sword, dirt block, mob spawner, whatever. And then we could have a final field for damage amount, where the wooden sword could do 3 and the diamond sword could do 10, for example. SQL stands for Structured Query Language. Structured Query Language. Structured Query Language. Now, the reason I say that immediately after doing databases is because SQL is the language that we use to query a database, to ask a database questions, to show things from a database. Now, the big three SQL commands that we would use would be select, from, and where. Select, from, and where. Select, from, and where. Select, from. The reason that I say that over and over again in that order is because in the exam, you will be expected to get it in the right order. If it's in the wrong order, the code won't work! Remember sequence from before. It has to be perfectly sequenced. Now, you're rightfully asking, Mr. Singer, what the flip do these commands do? Select chooses what fields to show. So, for example, if we did select customer name from the table customers, we would show all of the customer names from the table customers. By the way, you can use a star to select all fields. So that would bring back the customer's name, their address, all that sort of stuff. The from command chooses the table that we want to look at. So again, with the same example as before, if we had select customer name from customers, we're saying, I want this table, the customers table. This is where I want to pull my records from. This is where I want to show data from. Finally, you can think of where as an if statement on steroids. Let's use the same example again. Select customer name from customers where country equals United Kingdom would be a good example. Remember your quotes if you're doing a string, by the way. No quotes if you're doing a number.
Really? What you saying? Really? You're being random again. Stop being random, Philip. You need to be more predictable, Philip. Stop being random.
In the same way that Philip can be quite random sometimes, our programming languages can use special techniques to make random numbers. Now, OCR aren't very specific about what they mean by quote-unquote random number generation, so I'm going to give you a brief overview. Most programming languages give you the ability to produce a random number between two values. In Python, we do this using the random module by doing import random at the start of our code. And then to access that integer, what we would do is very simple. Random dot randint bracket the number at the bottom end, comma the number at the top end. For example, 0,9 if I wanted a number between 0 and 9. End bracket, end bracket. It's that easy. That would produce a number between 0 and 9. And if I wanted to put that into a variable, I could, same way as I would with any other integer. And if I wanted to print it, I could, same way as with any other integer. It's very, very simple, really. Section 2.3. Producing robust programs. We're going to make it robust. Section 2.3.1. Defensive design.
Philip! I'm trying to get onto our online banking.
Deborah, have you forgot the password?
Yes, Philip. What's the password?
You can't gain authentication onto the account without the password, Deborah. You can't authenticate.
first thing we're going to look at is authentication. If you don't understand this by now, I can't help you. Authentication is the idea that we have a username and you guessed it, password, in order to get into an account. That's it. I mean, there might also be like 2FA, two-factor authentication, and biometrics with fingerprint scanners and Face ID. But the main idea is certain users need passwords or other means to get into their account. That's authentication. Very quick, we're going to look at the big 5 of defensive design. The big 5. In an exam, you might be asked, here's a scenario, here's a client, here's whatever. Name 2, 3, 4 ways that they could use defensive design. Now, these are the big 5. Remember them, use them. Input sanitation. Just like sanitizing stuff in real life, it's getting rid of unwanted data. Cleaning up input data, getting rid of unwanted data. For example, removing special characters from a username box to prevent SQL injection. Sanitization prevents SQL injection. It's the reason you can't do SQL injection all that much anymore, because most websites have sanitization. Validation. Checking whether input data should be allowed based on a certain criteria. For example, your username box can't be empty when you're entering a username. Verification is checking whether data is being entered correctly. Checking whether data has been entered correctly. For example, when you have to do, you have to type your new password in twice when you reset your password.
For example, when you have to do, you have to type your new password in twice when you reset your password.
That's verification. That's verifying that you've typed it in right. Authentication, we've talked about this a little bit, is ensuring that only allowed/authorized users can gain access. For example, typing in your username and password. Maintainable code. This is number 5. Last one. To allow other programmers to understand the code. This keeps the program safe, because then any issues can be fixed. For example, comments, indentation, and meaningful variable names. Comments, indentation, and meaningful variable names. Those are the big 5. Anticipating misuse and input validation. Now, the idea is that good developers, good programmers are going to know what mistakes their users are going to make, and they're going to make the program in a way that can cope. There are many generic ways of doing this, but the 5 big validation types are as follows. To validate an input, like for example a password or a username when you're signing up for a website, the first check we do is a presence check. Now this ain't no Santa Claus, this is presence with a C, and it means to make sure that there's actually something in the box. Make sure that the box ain't empty. Next one is a length check. Let's make sure it's not too long and it's not too short. The next one is a type check to make sure the correct data type has been entered. For example, if you were asked to put in your age and you wrote a string, the word coconut, the program's going to know immediately that that's not right. Type check for data types. Format check. Now this is more appropriate to dates, to be honest, but any specialised data might use one. Let me give you an example. In America...
I thought this was America! Huh? Isn't this America? I'm sorry, I thought this was America!
They do their months before their days, don't they? So if it was the 7th of January 2023, they would do 01/07/23, whereas we would do it correctly 07/01/23. The format check, make sure the data is in the right format, because that could cause some real problems. And finally, range check. Now, this applies more for numbers than anything else, but it's worth noting. Let's say that you had to put your age in to buy a game on Steam, and we needed to make sure that your age was between a certain range. Let's say we're looking at teen games, we filtered by teen. We'd make sure the age was, above 12 and below 16 or whatever, because we wouldn't want mature games going to them. It makes sure the value's in a specified range. Right, we're going to finish defensive design with something called maintainability. This is in direct reference to code. Now, there are a few ways of doing this. The first way is with comments. Comments/annotations. The purpose of these is to explain key functions/sections of the code. Any relevant example would be appropriate here. I'll give you a little one. If you had num1 equals 4, you could do a little comment next to it with a hashtag and say num1 is an integer and the value is 4. Easy peasy. Next one. Indentation. Indentation shows where constructs/sections start and finish. For example, if statements. Whenever we make an if statement and there's the little indent to show that this is part of that if statement, that's indentation. The next one is meaningful variable names. Now, if I've got a variable that stores the number of kills I've got in an online shooting game, I'm not going to call that variable banana boat 123.
Banana boat 123.
That wouldn't be meaningful. I'd call it kills or, KD or whatever it might be. Next one is using constants if we can. Now, there aren't a lot of cases where you can use a constant, but if you're given a piece of code where a constant would work, then absolutely do it. If you've got pi or vat or something that could be the same throughout the entire program's run, then do it. That's it for code maintainability. Comments, indentation, meaningful variable names, and constants. Boom! Section 2.3.2. Testing.
Philip! Philip!
What, Deborah?
You've left your shoes in the living room again!
I know, Deborah.
Are you trying to test me, Philip? You're really testing my patience, Philip.
Philip can test Deborah's patience, but we as computer scientists should be testing our code, our programs. And the first section of testing is just that, the purpose of testing. What are the purposes of testing? All right, remember these. Number 1, check the program meets user requirements. Check the program meets user requirements. What does that mean? That means making sure your program does what the person who asked you to make it said that they wanted it to do. For example, if somebody commissioned you to make a website that sold aquatic mammals like otters and stuff, and you made a website that sold Bitcoin, you wouldn't be meeting the user requirements, would you? No. Next one, number 2, check the program works as intended. Actually, just make sure it works. Are there any logic errors and stuff like that? Speaking of logic errors, the third one, check for logic/syntax errors and allow these errors to be fixed. That's a massive part of it. If we test our program before it gets shipped out, we can fix what's wrong with it before it gets to the user. Unfortunately, EA didn't get that memo, nor did most AAA developers. I'm looking at you, Apex! Most games come out totally untested and they leave the testing to the players, but the proper way of doing it is to test it before it goes out. Number 4, check the program does not crash, in brackets, under invalid entry. Now you're going to say, Mr. Singer, that reminds me of validation that we did quite recently, and it's very, very similar. We're going to make sure the program doesn't crash under invalid entry. Imagine we had a system, like a web page, where we type in the number of quantity we want for an item. Say we're buying a pair of brand new Nikes.
Look at his eyes, look at his pupils. Beautiful. He runs brand new Nikes.
Imagine we wrote the word banana in the quantity box. Does the program crash, or does it just, does it validate it? Does it check that that isn't appropriate? That's the purpose of testing. Let's look at the 2 types of testing. One is iterative, which, by the way, if you couldn't figure out, is similar to iteration. It's one we do during development. It repeatedly tests the code while we're making changes. That's what it means. As you make it, test it. It's very, very simple. The next kind of testing is called final/terminal. Remember, this is a morbid comparison, but a terminal illness is one that causes the end. So a terminal test is one that we do at the end. Final/terminal testing is where the development is almost finished, and we do this after iterative testing. So at the very end, just before we give it to the person. The 2 types of error, syntax and logic. Now I'm going to be just totally straight with you on this. Syntax is an error in the grammar of the program.
Syntax is an error in the grammar of the program.
For example, missing quotes around a string, or forgetting the equals when you're doing an assign. Anything that's to do with the grammar, anything that gives you, and this is the easy way to remember it, a red squiggly line. One other way of saying it is it contains an error, but it will not run. It will not run. A syntax error won't let you run the program. The second kind of error, a logic error, is a lot harder to spot, and you need to use your brain.
This is big brain time.
A logic error is defined as so. Here's the definition. Code runs but doesn't do what it's meant to. For example, if we had a function called add2nums that actually subtracted 2 numbers instead, that wouldn't give us a red line. The program would still run, wouldn't it? But unfortunately, it wouldn't be doing what it was meant to. So that would be a logic error, when the program doesn't do what it's meant to. The 3 types of test data. Whenever we're testing a system, we need to test it with the 3 main types. These are the three. Normal, erroneous, boundary. Normal, erroneous, boundary. Normal, erroneous, boundary. What do they mean? Normal, expected normal data. Just data that the program would expect. If you were inputting your age, for example, normal data would be an integer no smaller than maybe 1 and no bigger than 120. That would be normal data, because I think that's the oldest recorded age in history, in modern history anyway. Erroneous data that would cause an error. So, for example, if, again, let's go back to the quantity example from Amazon or eBay or Apple or whatever. If you're buying 5 pairs of brand new Nikes,
Super Mario Sunshine, look at his eyes, look at his pupils. Beautiful. He runs brand new Nikes.
and you put -5 in there, or even the word banana, that would be erroneous data, because it doesn't actually make any sense. It'd cause an error. Erroneous, error. Notice the spelling. Boundary is data that is simply too big. Let me give you an example. Imagine that Amazon only had 100 pairs of fresh new Nikes on their site, and you tried to order 10 billion. That would be a boundary, a piece of boundary data entered, because that is way, way too many. Way too many. A boundary goes too big. That's it for testing. Bish, bash, bash. And, or, not. These are the 3 main gates that you will use in your GCSE paper 2. They are Boolean logic gates, and you must know them off by heart. The questions can be big and they can be nasty. Start with the shapes. The AND gate looks like a big letter D. Capital, by the way. I remember it because AND has a big capital letter D at the end of it. OR looks like an arrow. Like an arrow, like a pointy head of an arrow. 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 The NOT gate is a triangle lying on its side with a little circle at the end. Whenever you see that little circle at the end, you know it's negation. It's a NOT gate. Now, let's go through these gates together. AND gate, let's look at the truth table. And we're going to use A, B, and C as our inputs and output, respectively. A and B are the 2 inputs, and C will be the output. If 0 and 0 go in, we get 0 out, because both inputs need to be true for us to get a true result. That's why it's called AND. This and this must be true to get a true result. 0 and 0 makes 0. 0 and 1 makes 0. 1 and 0 makes 0. 1 and 1 makes... Come on. 1. Well done. The OR gate is a little more forgiving. If either of the inputs is true, we get true. And this also applies if both are true. So, with a 0 and 0 on the A, we get 0, because neither are true. With a 0 and 1 on the A and the B, we get a 1, because this or this is true. With the third one, 1 and 0, we get 1, and 1 and 1, we get 1. Hoorah! Last one, the not gate. Oh, this scares me, it scares me. Stop making that noise, Philip. The not gate is the easiest one. Whatever goes in, the opposite comes out, and it can only have one input. If you put a 0 in, you get a 1 out. And if you put a 1 in, you get a... Well done! A 0 out. Hola, soy Dora. Section 2.5 Programming Languages and Integrated Development Environments. Section 2.5.1 Languages. Hola. No, I'm not going to do it. No. No. Okay, we're not looking at Spanish. We're looking at the different types of language that exist. And there are two main ones. The first one is like me, low level, quite close to the ground. The second one is high level. So you got low level and you got high level. Let's look at low level first. Low level is, and this is the definition, difficult to read and understand, requires understanding of the process's registers and structure, and can make more efficient code if the programmer knows how to use it. But high-level code, on the other hand, is easy to read and understand. There's less code to write, because one high-level instruction represents many assembly instructions, or low-level instructions, uses English-like keywords, such as print and while, for example, must be translated before the processor can execute it. The code written is portable and can be used on different processors. Now, you say, Mr. Singer, what the flip is a low-level language and what the flip is a high-level language? Well, we'll do the high-level first. Python? Python's a high-level language. You see those English words there? See how it's quite easy to understand? That's great. Low-level will make you want to pull out your own soul and barbecue it, because it's so unbelievably difficult to understand. Low level uses what's called assembly code. Assembly code, which is a mixture of lots of three-letter mnemonics, like STA, LDA, SUB, ADD, etc. It's very difficult to write with and very difficult to understand. In fact, we don't really do any coding of it until A level because it's so hard. But high level is very, very easy. So again, examples of low level, there's only one I can think of for the sake of GCSE anyway, and that's assembly language. Assembly language. Whereas with high level, there are many. Python, Java, C#, C++, etc., etc. Some advantages of a high level would be it's easier for humans to write, it's easier for humans to understand, and it's easier for humans to maintain or spot errors, which is great. There's also less code to write in a high-level language because one high-level instruction represents many assembly instructions, and it's portable, so different processors can use the same code. Because when you write a Python program and you take it over to your mate's computer, it works, doesn't it? Even though it might be a different computer, maybe even the computer at home and the computer at school, they all run with Python because it's portable. But if you did that on assembly for your processor, oh my goodness, it would not work because low-level code ain't portable. Translators. A translator is needed. Listen to me because this is the definition. A translator is needed to convert high-level code to machine code / binary. This is because CPUs only understand machine code. One more time. A translator is needed to convert high-level code to machine code because CPUs only understand machine code. A nice example of this would be whenever you press run on Python, you're converting your high-level code with all that English that the processor can't understand with the for loops and the whiles and the prints and the comments and all that sort of stuff. And it's converting it into machine code that can be understood by your CPU. Boom. Compiler and interpreter. You've got to ask the question, yeah. You're doing your program. How the heck is it finished, you know? How does it become, like, how does it go from code to actually being a program that someone can, like, click on and open? Well, this is the question. There are two ways of doing it, pretty much. One is a compiler, one is an interpreter. Let's look at the differences, and I'll give you an example for both. Hands up if you've ever opened a program on a computer, like Word or PowerPoint. Well done, you just opened an executable. Compilers create executable files that we can open, and they do it all in one go. This is the definition of a compiler. Listen to me. A compiler translates all the code in one go. A compiler creates an executable, a .exe. Compilers report all errors at the end, not during. Now, an interpreter translates not in one go, but one line at a time. A compiler makes an executable, but an interpreter does not. The interpreter executes one line at a time. And finally, instead of reporting all the errors at the end, an interpreter stops when it finds an error. Now, you're saying, Mr. Singer, you've given me an example of an exe, you know, what a compiler makes, an executable, but you haven't given me an example of an interpreter. Have you ever used REPL or IDLE or any other IDE? Every second you were typing, the interpreter was going through your code line by line, checking for errors. It didn't make any file, but it was going through and making sure it worked. The most common use for an interpreter is error checking in an IDE. And the most common use for a compiler is creating an executable file. Well done. Section 2.5.2, the Integrated Development Environment. IDE. In the exam, you're probably going to get tested on the features of an IDE, or the tools of an IDE. Means the same thing. There are 5 big boys. Let's address each of them individually. Number 1, an IDE contains a text editor, an editor. This enables us to program code to be entered and edited. Think about REPL, you know, the part where you type in your code? That's the editor, because you can edit it. That was pretty simple. The next one is error diagnostics / debugging. This shows us information about errors, syntax or runtime errors and their location, what line they occur on. It also suggests solutions. Runtime environment. This enables the program to be run and lets us check for runtime errors. Every time you've ever pressed the play button in idle or on REPL, you've used the runtime because you've run your program. It lets us run the program. Breakpoints. Now, we use these a lot more at A-level. You probably haven't used them yet at GCSE because your programs aren't that complicated, but I can assure you they get very, very useful. Breakpoints are little stops you can put at the side of your code to make your program pause on a certain line. Here's the definition of a breakpoint. Breakpoints: pause program execution at a specific point. You might be thinking, Mr. Singer, why is that useful? Well, think about it. If you've got an error on a certain line or something's broken in a certain part of your code, you can pause the program just before that break and you can see what's wrong. Dead useful. Finally, keyword highlighting / color coding keywords. If you've ever used REPL, which you have, or idle or whatever, not so much in idle kind of sucks, but in REPL, print statements are purple, which looks really nice. While loops are blue. Variable names are black. Color coding our code makes it easier to read and easier to write.
Philip! The students are about to go for their exam! Say something nice!
Right, kids. You're gonna go in that hall and you're gonna get mentally desecrated. Prepare as best you can. Use this Spotify playlist. Use your revision guide. And get yourself as ready as you can be, because this exam board ain't exactly predictable. Try your best.
I echo Philip's sentiments here. Go for it. Do your absolute best. You can get that 9. Everything you need to get a 9 is in this guide and in the revision books. Give it everything you've got and you will crush it. Now go for it.